Alrighty, section 2.2. Nice. Alright, so in this one we're going to talk about limits. We're going to look at them from a graphing standpoint, okay, and through a numerical standpoint. The numerical standpoint, you're going to say, well, looks an awful lot like what we did when we did instantaneous rate of change. And you're right, it is very similar to that. And so the idea of a limit, the definition of a limit that I'd like you to know is this. It is the value that y approaches as x approaches a particular value. Now, in the case of some boring functions, value. In the case of some boring functions like a linear function, here at x equals 3, as your x's get closer and closer to 3, and what do you mean by that, Jay? Well, I mean, well, you could start with 3.5 and plug it into this function, and then you get a y value out. Let's say it was 1.2, and then you go, well, I can get closer, Jay. 3.3, 1.1, 3.1, 1.09, 3.0001, 1.0001, and you're like, well, I can come at it from the other side too, and well, of course you can. 0.9999, and I can get further away, and of course you can get further away with these guys. And the idea is that as you approach 3, this guy here in the middle, your y's are approaching. So as your x's get closer and closer on either side, your y's are approaching some value right here. In this case, it's obviously 1. And so, we would say that the limit, this is how we'd write it, we'd say the limit of f of x as x approaches 3 is 1. That's how we'd say it. And that's how we'd write it. Now, we're going to do a boatload of these. I need to pause for a minute. Now, interestingly enough, when we say the limit, what we really mean is the limit. Now, why do I write it like that? It's because the sounds like a unique limit. And that's the idea. Okay? It's unique. So when we say the limit, it has to be the same. Y has to be approaching the same value regardless of what side you're approaching it from. And what I mean by that is this. You could have a function that comes up to here. Here's x equals 1. And so as you approach it from this side, it sure looks like the y's are approaching approximately y equals 2 here. But if you approach it from this side, it looks like it's approaching 4. And so there is no one unique limit. Okay? So in this situation, we would say the limit as x approaches 1, again, if this whole function is f of x, we say the limit does not exist. However, if you take the limit as x approaches 1 from the left. Now, a little negative sign means from the left. So as you're coming from this direction, the y's appear to be approaching 2. Okay? And as you approach it from the right, they appear to be approaching 4. And so we're going to have some definitions. This guy right here is what we call the left-hand limit. This guy right here we call the right-hand limit. And the idea here is this. The limit only exists if the left-hand limit equals the right-hand limit at the point in question. What I mean by that is this. Over here at -1, what is the limit? I don't know, 1.5. Because as you come closer this direction, it's nice and smooth right there. You go through this point, which is clearly like y equals 1.5. Now, let's write this in big kid terminology. So, it says this. If the limit as x approaches a from the left of some function is equal to the limit as x approaches a from the right, then the limit as x approaches a of f of x exists. Exists. Okay? Now, this is really truly an if and only if statement. Now, you may have heard that at some point in the past, if and only if. Now, what does that mean? It means it works both ways. And in math, we sometimes abbreviate it this way. Okay? If I tell you that the limit exists, if I say that this is true, okay, so if I say if this is true, then you know these guys are true. That's what if and only if means. It means you can put the if and thens in either direction. Okay? If and only if. It works in either direction. So, we'll see a couple other places where that happens. Continuous functions is another definition of a continuous function, rather, the definition of continuity is another place where that will show up later on, and you'll see what I mean by that when we get there. Okay? Now, let's look at some more functions here. Okay? Ooh, it's an asymptote. How cool is that? Whee! Whee! And here's x equals 1. What happens to this function? Again, this whole thing is f of x. What is the limit as x approaches 1 of f of x? The limit as x approaches 1 of f of x does not exist. And the reason it does not exist is because coming from this direction it goes down. Coming from this direction it goes up. Okay? But if I said to you, hey, what is the limit as x approaches 1 from the left, you would say it's going to positive infinity. And if you said that the limit as x approaches 1 from the right, you would say, why, that's going towards negative infinity. Pretty straightforward deal. Okay? Ooh, here's one. This one always trips people up. Oh, there's a hole in my function. There's a hole in my function, dear Margaret, dear Margaret. What is the limit? Let's be fun this time. Let's do g of x. What is the limit as x approaches 2 of g of x? So here I come. I'm headed towards, I'm going to make that 3. Okay, I'll make it 4. There we go. Cool. So as x approaches 2 right here, what are my y's getting closer and closer to? It sure looks like they're getting closer to 4. Now the astute observer realizes that this is a hole, and the function doesn't exist there. But picture yourself walking down this thing with a blindfold on. Look like Robin. There you go. You're walking down this function. You keep putting one foot in front of another, and you keep taking little baby steps. Here I am at 2.0 or 2.1. At 2.1, the function is equal. It's there. I'm here. It's fine. 2.1. All right, let's move a little closer to 2. Let's go to 2.09. Hey, the function's still there. And I'm getting closer and closer and closer. And every time I get closer, these y's are approaching 4. And for all I know, when I get to x equals 2, it is going to be 4. It doesn't matter if the hole is there or not. It has no impact on what the limit is. The limit is what the value seems to be approaching, or what it is approaching. It doesn't have to get there. It just has to approach it. Okay? So we're going to look at some graphs here on, I like to use Desmos. I think I've showed you that a little bit. To me, this is the software program calculator or otherwise. There is, as I think I've told you, an app for your phone that you can use. If you want to use the grapher on the phone, I do not care. It's a Desmos app. It's free. I don't know how to run it on the phone, so don't ask me. I don't really know. So let's do, I don't know, cosine of x. Hey, cosine of x, that looks pretty straightforward. So let's see what happens as x approaches 1. Okay? Well, as x approaches 1, the value you see is 0.54. But if you do this, you can take your pen like this and drag down. If this wasn't here, if this line wasn't here, you would sure go, sure looks like I'm getting awfully close to 1. My values are getting awfully close to, come on, give it to me. My y values are coming up and they seem to be approaching 0.5-ish. And you're like, but you can get closer, Jay. I know, so 0.5, 0.5, 0.54. Yay! And you can tell that, again, just by graphing and tracing on the function. And on a nice, beautiful function like this, where all the pieces and parts exist, you can see those numbers anywhere. However, and here's a big however, what happens at x equals 0? Well, now, first of all, at the first blush, it looks like it goes to the origin. So as you watch, as the x's get closer to 0, my y's are getting closer and closer and closer to 0. Uh-oh. There's a hole there. But as you come out from this direction, the y's are getting closer to 0. So on this function, we would say, hey, it looks like the limit as x approaches 0 of this function is 0. And again, that would look like this written out. We would say that the limit as x approaches 0 of 1 minus the cosine of x over x is 0. Okay. What about this fella? The limit as x approaches -1. Now, let's go look of it. Oh, shoot. No, did I do that right? Oh, yeah, I did it right. Good for me. So here it is. I'm approaching -1, approaching -1, approaching -1, and oh, dear. It's undefined. But look at the y's. The y's are awfully close to what? 2. And so we'd say that the limit of this function is 2 as you approach -1. Now, of course, that's different. What happens as you approach 3? I don't know. Let's go find out. You go look at the function again at 3. Why, it's 4. And the function actually exists there, so that's cool. What about the limit as x? Well, I'm just going to change this. What about the limit as x approaches +1? Well, as you approach +1, my y, wow, holy cow, they're going way down. And these ones are going way up. Why is that? Because when you put a -1 in the denominator, you get 0. Uh-oh. And so the idea is this one does not exist because it's going up on one side, it's going down on the other. So you would say that, well, I'm just going to write it here. So the left-hand limit, clearly from the picture, is going to -infinity. And the right-hand limit, of course, is going to +infinity. It's pretty easy to do. Right? Now, what if I wanted to do this in a numerical fashion? That same basic procedure, for instance. Let's do that 1 minus cosine of x divided by x. Suppose that was my function. Suppose I wanted to approximate this, what we call numerically. Well, if I'm doing that, I'm going to use Excel because, well, it's my thing. And again, I'm interested in what happens at 0. So I don't like screwing around. I don't know about you. I find it obnoxious. So if I want the limit at 0, I'm going to go right to the middle and do this. And so I'm just going to say equals this guy. I want to do minus 0.1 or something. And then I'm just going to drag that up. You can type these in if you like to. And then you could say equals this fella plus 0.1. And then drag that baby down a ways. Whee! And then you can go, all right, so my function was equals parentheses 1 minus cosine of x. Remembering that this is in radians, which is what you want always in calculus. And then you drag this baby down. Now that divide by 0 bit there, that means the function doesn't exist. That's a hole. We already saw that. Now you first look at that, you're like, wow, the numbers are getting bigger coming up this way. They're headed towards 0. These ones are getting smaller, headed towards 0. It sure looks like that should be a 0 right there, even though the function doesn't exist. And you're like, well, can I get closer? And I said to you, well, sure you can. Yeah, and it still looks like it's getting closer and closer to 0. Now that is okay, how I would do it. Now your book actually gives you some little oopsie daisy, some charts that are already filled out. So for instance, in this case, it would say something like this. It would say, find these values, and I think it does a little x and a little f of x action. And it gives you some ideas. Well, let's see, you can't put 0, but they would give you something like 0.1, and then negative 0.1, and 0.2, and negative 0.2, and so forth. And you're to fill in these blanks, and then try to approximate. What happens is you get closer and closer to 0. The same idea is with Excel, it's just not, I don't think it's as nice. Now, some people like to use their calculators. I get it. If you have them, good for you. And so on this deal here, I would go to y equals, and I type in my function. Again, notice that the rad here at the bottom of the thing there, it says it's in radian mode. So 1 minus, and it needs to be in radian mode, 1 minus cosine of x divided by x. Okay, and go back to the table. And then here's where it would ask you to put in some values, right? And you would just go 0.1 and negative 0.1 and so forth. You see that? And it's the same deal I had on the Excel. It's just a little trickier to get to. Ditto on the TI-83. So go to here, y equals, clear that, parentheses 1 minus cosine of x divided by x. Make sure that you are in the mode that you want. We want radians. That's true. Now go to the table. And here again, you can type in your values and so forth, and then you fill out the chart from there. Not very hard. They want you using that chart, I guess, so that you can see what's happening there. See what's up with it. You might even see one of these today. What is the limit as x approaches infinity of 1 over x? Now, most people go, I'm going to graph it, which is good. I heartily concur you should do that. What's happening to this guy as you head out this direction? It sure looks like my y's are getting smaller and smaller and smaller. They're headed towards 0. Oops. What some people might say is the answer is 0. And I would say to you, well, remember, the limit only exists if you can approach it from both the left and the right. Well, now wait just a cotton pick in a minute. For that to happen, you would have to be able to go all the way to infinity. You're walking up here, get all the way to infinity, and then get on the other side of infinity and come back. Bro, you cannot do that. That's infinity and beyond, which, by the way, does not exist. So, here's the game. We will only write it as the limit as Come on, stupid pen. We will only write it like I wrote it right here. But when it comes to infinity, this really means the limit as x approaches infinity from the left. Because that's the only way you can head towards positive infinity. That's the only way you can get there, is to come at it from the left-hand side. Ditto, when I say to you I want to move toward the negative infinity, which is way over on this side of the screen. The only way you can do that is to approach it from the right. Okay? And so we will never say these things. We'll never say that. We will just say the limit as x approaches negative infinity and the limit as x approaches positive infinity. They only have these two functions. That scenario when you're going to infinity or to negative infinity, okay, those are weird ones, but those guys only have one-sided limits. Okay? And that's just how it goes. Now, here's a fun one. What is the limit as x... so anyway, the limit... I shouldn't finish that up. So the limit as x approaches infinity here is 0, because it's getting smaller and smaller. Just be careful. Some people who actually listen and they go, well, wait a minute. There has to be... You have to be able to go from two sides. The difference is, of course, at infinity is a little different. Kettle of fish. All right. What is the limit as x approaches 0 of the square root of x? Not sure what square root of x looks like, so I come over here. Square root of x, square root of x is right here. Square root x. Oh, by the way, old school way of doing that was squirt, and that is actually how Excel does it. So they do square root of and then x. Okay, so it's squirt of x. Most computer programs, same deal. What's happening to this function as you approach 0? Well, it's headed towards 0. The y's are headed towards 0. What's happening on the negative side? Nothing. Oh, interesting. So, the limit does not exist. The only limit it has is the limit as x approaches 0 from the right, because that's the only side it exists on, and the answer is 0. Okay. All right, there's one last little piddly-diddly thing I want to show you. I will show you this because depending on who you have for your teacher, once in a while, they'll make this a big deal. Okay? I think it's something that's okay to know and do once or twice. We don't really ever use this. Okay? So the actual definition of a limit. Now you're like, well, that should work to find a limit. Ooh, au contraire, my friend. It only works, you can use it to show that a limit is this or a limit is that, but you have to have a value or a guess for what you think the limit is in order to pull this off. Okay? And so, the actual limit definition looks like this. So, when we do this, we say that, all right, so as x approaches c, that's what we've been saying, sort of. So, the limit as x approaches c of f of x is equal to L. Now, what does that look like on a graph? Well, here's L. It is just some y equals L. It's a y value. Here is x equals c. Something like this. Okay? So when I plug in a value, let's say that this is, I don't know, 1. If I plug that in, it's going to be some f of 1 right here, yes? And of course, if I plug in 2, let's say right here, that's going to be some f of 2. And what have we been doing? We've been getting closer and closer and closer and closer and closer, x-wise, and watching our y's get closer and closer. That's what we've been doing, right? Well, so what the deal is this. We're going to take f of x minus the limit. We're going to take the absolute value of that. Now, what does that mean? It means that we are a certain distance from the limit. Okay? And so we can get closer on the x, move the x over a little bit, come up. Oh, look, our y is closer to the limit. And we can get as close as we want to. Okay? Now, stay with me on this because this is where it gets a little weird. Okay? What we need to see is this. We need to be able to show that x minus c, that's this difference down here, right? Because here is an x value right here. This isn't an x value, just any random x value. So x minus c is this distance from here to there, yes? Okay. So this is how the game is played. So you're going to get given a function. So I'm going to say, let's let f of x equal 3x minus 1. And I'm telling you that I think that the limit as x approaches 2 is 5. That's what I think it is. So let's go look at the graph. Where would I get that crazy notion? Well, 3x minus 1. Look at that. Hi, George. I think it's 5. Seems reasonable, right? That seems reasonable. So in order to show that that limit actually works, what you're going to do is take f of x. So 3x minus 1 minus your proposed limit. Okay, so there's f of x minus this supposed limit. And what I'm going to do is this. That's going to give me 3x minus 6. Are you with me? Oops. Not parentheses, stupid. Absolute values. Now it occurs to me they have a 3 in common, yes? Yeah? What does that mean to me? What that means to me is this. Wait a minute. I see x minus 2. Do you see that? Because the limit in question, the number in question was x equals c, in this case 2. And I want to know how far it is out to the x in any x in question. Well, the difference would be x minus 2. Are you with me? And so because I can write this relationship, f of x minus L, because I can write it as some multiple of the difference in the x's, that is x minus the x equals c that we're interested in, because I can write it that way, 5 is indeed the limit. That's it. Again, you cannot find a limit this way, but if someone says to you, by George, I think it's this, you can show that they're right or they're wrong. Now I'm going to do another one that works, and then we'll do one that's gross here in a minute. Okay? So x cubed minus 3x plus 1. Let's take a look at the limit as x approaches 1. And I think that it's going to be negative 1. Oops. I am proposing to you that it is in fact negative 1. And you say, okay, let's do it. So it's going to be x cubed minus 3x plus 1 minus a minus 1, always because it's minus, and then because that's negative 1, over x minus 1, because again, the difference from x to 1 is x minus 1. Oops, I'm sorry, I don't mean to divide out by that. I'm sorry, I was thinking of something else. Don't divide out by that, just keep that in your pocket for a minute, okay? So this becomes x cubed minus 3x plus 2. Now you're like, well Jay, that feels weird. What am I going to do with that? I made this kind of a hard problem. I didn't mean to. The game is that this thing here has to be able to be written as x minus 1 times something else. Are you with me? Has to be able to be done. This something else is what I need to find. In order to do that, I'm going to have to do long division. And so I guess we'll do a couple more of these because these are, maybe it's been a while since you've done them. How many times is x going to x cubed? Why, it goes in x squared times. X squared times x is x cubed. X squared times negative 1 is negative x squared. If you subtract, you get x squared minus 3x. How many times is x going to x squared? Why, it goes in x times. X times x is x squared. X times negative 1 is negative x. That becomes negative 2x plus 2. X goes into negative 2x, negative 2 times. That becomes negative 2x plus 2. When you subtract, you get 0. That means it goes in perfectly. So what we have then is this, x squared plus x minus 2. We have that times this. Okay? That means we can write this as x plus x minus 2 times x minus 1. And because it's a multiple, right here, of this guy, then in fact it is actually the limit. I won't give you anyone that hard on the test or the homework either, so I'm going to do a nice easier one, and I apologize. I really wasn't know what I was thinking about right then. It's not going to kill you, but it's not too fun either. Let's see what happens at x equals 2. So if as x approaches 2, rather. So I submit to you, I think that the limit of f of x as x approaches 2 is negative 11. Well, if that's true, then this guy should be able to be rewritten as something times x minus 2. X squared minus 7x plus 10. Plus 10? Nope, that's right. I was like freaking out. Why isn't that working? It is working, dummy. Pay attention. So this inside factor is x minus 5 and x minus 2, correct? Which of course can be rewritten as this guy here times this guy here. And because it is a multiple of this guy, okay, then it is in fact a limit. That's all there is to it. It's not very hard. Don't overthink it. It really is just not a big deal. That's all you're going to be showing when you're doing these guys. If it seems a little weird in that, you know, you're honing in on something and you're just kind of like, well, can I put any number in there? Well, yeah, it should work, except, watch this. What if it wasn't correct? What if this was like 7? Well, then this would be straight up minus 7. Okay. Oh, shoot. Which would make this x squared minus 7x plus 8. Does that factor? It does not factor. And even if it did factor, x minus 2 is not one of the factors. And because x minus 2 is not one of the factors, it is not the limit. That's it. For instance, this could have been plus 6. Okay, let's see how I would have had to have done that. If I would have said it was 5... Oh, that's even grosser because it doesn't work. It should have been negative 8, but it's still... Oh, wait, negative 8, that would have worked. Let's try it again. This is actually good. So leave it as 7. That was what it should have been. Okay, cool. Then this is even better because somebody says, hey, that factors, Jay. You're right, it does. But you know how it doesn't factor? This guy isn't one of the factors. If this guy isn't one of the factors, then 7 is not the limit as x approaches 2. That's it. That's all you can say. Okay? So some teachers, some professors just think this is the end all and be all and the coolest thing ever. Honest to God, it's really not. Okay? It's nice that it kind of forms the background of it. Limits are so important. Being able to see them graphically, numerically to some degree, algebraically later on, And then most importantly, the limit laws, how they function, what are the rules for them. If you understand those things, then everything else from now on going forward is great. If you have a hard time doing this little rigmarole here and you think, oh, I'll never be good at it, wrong. This is not important that a person can do, really. It's something that some people need to see. I think it's enlightening to look at it a couple times for me, but that's because I'm a math teacher. Okay? Some guys really just go nuts on this stuff and think it's the end all and be all. And honestly, I just don't think it is. You can be a great user of calculus. Maybe not a great mathematician if you don't really understand the concept any better than that. But you can really understand the limits inside and out without understanding how to play this little rigmarole with the limit definition.